Alright, we're going to go ahead and get started with Lecture 3 in our chemical bonding unit. We're going to address the topic electronegativity here in this lecture. Electronegativity is an important topic, so make sure that you very much understand this concept before you're done with this lecture, and know the periodic trends of electronegativity within the periodic table. Okay, so here are the essential questions for this lecture that need to be addressed, and you need to be able to answer by the time you're done with this lecture. So how do we use bond enthalpies to calculate the enthalpy change of a chemical reaction? What is electronegativity? How do you predict whether a compound of two elements would form a covalent or ionic bond? Okay. So let's start out with discussing bond length. Below is a good definition of bond length that should go into your notes. The bond length is a measure of the distance between the two bonded nuclei. Let me draw a quick diagram for you. Let's say we have one atom and its nucleus, and another atom which will overlap to share its electrons. Here's the other nuclei here. And the distance between these two nuclei right there, that distance is known as the bond length. Alright, so there's just a quick diagram you can put into your notes. Alright, so on this, we're going to use this table here, table 8.5, that shows bond lengths to answer some basic questions here. What I want you to do is focus on an important pattern. If we look at the length of this carbon-oxygen triple bond and carbon-oxygen double bond and single bond here, you should notice that the more bonds that exist between two atoms, the shorter the bond length. So in your notes, what I want you to write down is that double bonds have shorter bond lengths than triple bonds have shorter bond lengths than double bonds, and double bonds have shorter bond lengths than single bonds. And you should be able to pretty much see that within the trend of this table. So make sure you get that down. Alright, now, number 3, determine the bond lengths for each bond for the above molecule. Now, I'm going to let you kind of do this on your own, but if we take a look at this carbon-carbon bond, you should be able to look at the reference here up in the table and see that a carbon-carbon single bond there has a bond length of 1.54 angstroms. So that's just basically how you use a table like that. Determine those bond lengths between those bonded atoms. Alright. Let's move on. Alright. A more important topic than bond length is the strength of chemical bonds. Typically, when we look at the strength of a chemical bond, we look at it in terms of what is known as bond enthalpy. And bond enthalpy is purely a measure of the energy required to break a chemical bond. And so what we find as a trend is that multiple bonds between atoms are harder to break and therefore are referred to as stronger bonds. So what exactly are we looking at a multiple bond? Well, for instance, a triple bond. So if I have a carbon that's triple bonded to another carbon, it's going to take a lot of energy to break those three bonds. And so a triple bond is quite strong. Compare this to a double bond. A double bond is not as strong, so I'm going to put a greater sign representing that it takes more energy increases in order to go from a single or a double bond to a triple bond, and we can also put in a single bond. A single bond is going to be the easiest to break, so we can also say strength bond strength increases as we go from single to double to triple bonds. So again, single bonds are the weakest and triple bonds are the strongest. Alright, so as far as bond enthalpy is concerned, a good definition of bond enthalpy is right here. Put that in your notes. Bond enthalpy is the energy needed to break 1 mole of bonds in gaseous molecules under standard conditions. I would almost know that word for word. Most students make the mistake of forgetting the gaseous molecule part in the standard conditions for this definition. So pay attention to that. Alright, 2 other really important points are these right here that should go into your notes. When we break a chemical bond, it is an exothermic process, meaning it requires energy to break a chemical bond. And when we make a chemical bond, it's an exothermic process, and energy is going to be released when we make that bond. Alright, so go ahead and put that into your notes and keep that in mind as we get into this next idea of calculating delta H from using bond enthalpies. Alright, so we've kind of already talked about this using Model 2, which is this table 8.4, describe any patterns within the data. So let's look at the data on this bond enthalpy table here. So the things I want you to pay attention to is, first of all, these are the average bond enthalpies in kilojoules per mole. These values right here are the energy needed to break those particular bonds. So for instance, if you look at a CH bond right there, it requires 413 kilojoules per mole of energy per mole of chemical bond in the gaseous state to break it. Alright, and so that's pretty much how you use that table. Now, as far as some trends, again, going back to bond strength here, if you look at these two down here, you'll notice that it takes more energy to break that carbon triple bonded oxygen than the carbon double bonded oxygen. It takes 1072 kilojoules of energy to break the triple bond, then 799 kilojoules of energy to break the carbon double bonded oxygen. Alright, so just kind of think about those in the data trend there. Alright, so what we're going to do here is something that arises quite a bit on both the AP and the IB exam, and that is using bond enthalpies to calculate the delta H of a particular chemical reaction. So I'm going to model how to do this and show you an example problem, and then in class we're going to work through some of these problems or types of problems so that you can practice them. Alright, so let's take let's look at an equation. Let's say we're going to have a reaction of hydrogen gas plus oxygen gas, and it's going to make 2 moles of water. Okay? Now, in order to use bond enthalpies to calculate the delta H of this reaction, and I'll remind you real quick, remember we can use calorimetry to find the delta H value, or we can use Hess's law, and now we're going to learn how to use bond enthalpies to calculate the delta H of this reaction of producing water. Okay? So we're doing a little bit of thermodynamics here. The first thing you have to do and use bond enthalpies is you have to write the Lewis dot structures for each species that's in the reaction. So I'm going to do that real quickly. So you have 2 moles of hydrogen gas, so that means we've got 2 of these. And there's the Lewis structure for that. Plus the oxygen, here's the Lewis structure. I'm going to leave out the extra dots for right now just to make this simple, but you would want to include those dots on the test or quiz. And you're going to create water, but you're going to create 2 moles of water. Write those out like so, okay? So there's the Lewis dot structures for everything in this chemical reaction. Now, what we need to do in order for this chemical reaction to work is we have to break these bonds here. They have to be broken. And the bonds in the water molecules between the hydrogens and oxygens have to be formed. And so we already said that in order to break a chemical bond, it requires a certain amount of energy. And then if we make bonds, it releases energy. So in order to find the delta H for this reaction, we have to take, and here's the equation down here at the bottom, we have to take the sum of the bond energies for the bonds that are broken and subtract that from the sum of the bond energies for the bonds made. In other words, we're going to take the energy of the bonds broken minus the total energy of the bonds made. And so to use that, we're going to use our table over here, 8.4. So if you look closely, we have to break 2 bonds, 2 HH bonds, okay? So I'm going to start writing this down. The delta H for the reaction is equal to 2 moles, or 2 bonds of the HH. Now, if you look here, the HH bonds, look in your table really carefully, and you should find the HH bonds right there. It takes 436 kilojoules of energy to break it. So 436. And then we need to add that to the amount of energy to break the oxygen double bond, which is right there, 495. So we're going to add that to 495. I have to squeeze that in there. Alright? And then we're going to subtract all of that from the bonds made. Alright? And that's from these bonds, the oxygen and hydrogen bonds here in the water molecules. And so we're making 4 of those, 4 OH bonds, and we can find those right here. So it takes 463 kilojoules of energy to break those bonds. Alright? So now all we need to do is the math. And if we do the math, we should come out with a delta H of this reaction to create water should equal a negative 485 kilojoules of energy. Alright? To formulate 2 moles of water. And that's all there is to it. So again, all you have to do is take the total amount of energy to break the chemical bonds minus the total amount of energy that's released when we make bonds. And we can get all of those values in a table like this. And you're going to see this on your exams and quizzes. And again, we'll have some practice on how to do this and so forth. Alright? Alright, so now we're going to move to a new topic. We're going to get into the heart and soul of this lecture, and that is electronegativity. And this, again, as I mentioned at the beginning of the lecture, is really a valuable concept to understand. So make sure that before you come to class, you really know what electronegativity is. Alright, so down below here is a good definition of electronegativity. Make sure you have this definition in your notes. Electronegativity is the ability of an atom to attract electrons in a covalent bond. Alright, so if I was to kind of demonstrate this really quickly, we're going to make our covalent bond here. Here's the nucleus, here's the nucleus, and then it's going to share 2 electrons between those 2 nucleuses. Right? Now, these 2 atoms are both attracted to these bonding electrons. So electronegativity is going to be the measured attraction of these bonding electrons between the nuclei. Now, both of these atoms, if they're the same atoms, are going to have the same attraction for those bonding electrons. But if they're different atoms, then one atom is going to have a stronger attraction for those electrons than the other. And that's where electronegativity values come into place. And I'll show you that here in this table. This table shows all the electronegativity values for the atoms that we are going to concern ourselves with. You will notice that in this periodic table there is no noble gases here, and that's because noble gases really don't form chemical bonds, so they don't have an attraction for bonding electrons at all. Alright? They don't have a desire for electrons because they're not bonding them. Right. So let's look at question 2 here. It says, what is the general trend in electronegativity as you go down a group in Model 3? Support your answer using examples from the 3 groups. Okay, so we're looking about the electronegativity trend as we go down a group. So let's take group 1, for instance. Let's look at group 1. What's happening to the electronegative value? Well, if you look closely, you can see that hydrogen is 2.1, lithium is 1.0, sodium is 0.9, and so forth, and it looks like it's decreasing. So, according to group 1, electronegativity decreases as we go down. Let's look at group 2. The same trend applies in group 2. Let's go way over on the other side to the halogens, and yes, we see the same thing. So it appears, according to the periodic table, as we go down the periodic table in a group, the electronegativity is going to decrease. Alright, so that's really important. Alright, so now, just like when we talked about in the periodicity chapter, why we had to look at periodic trends for ionization energy and atomic structure, atomic radii. We also need to know why the trend for electronegativity is occurring the way it is. So number 3, it says, using your understanding of effective nuclear charge and structure of the atom, explain the trend in electronegativity that identified in question 2. And the best answer is down here at the bottom here, where it says bonding electrons are furthest from the nucleus, and so there is a reduced attraction. So what that means, of course, is that since we go down the periodic table in a group, electronegativity decreases. It's because the bonding electrons are getting further from the nucleus, and so the nucleus has a less attraction on the bonding electrons. So francium, its bonding electrons would be clear out there in the valence shell of period 7, so n equals 7, or the 7th energy level, and so those bonding electrons are quite far away from the nucleus. So francium has a very low electronegativity, or doesn't really attract to bonding electrons. However, hydrogen has a little bit greater attraction, being 2.1 electronegativity. All right. So now let's look at the trend as we go across the periodic table. And it says, what is the general trend in electronegativity as you go across the periodic table left to right? In Model 3, support your answers using examples from 2 periods. All right. So let's take a look at this. Let's look at period 3. It appears that as we go across period 3, the electronegative value increases. Same thing with period 4. The electronegative values are increasing. So it seems then electronegativity increases from left to right as we go across the periodic table. So why does that happen? Why is it increasing as we go across? Well, it's simply this. The nuclear charge, let's go back. The nuclear charge increases going from left to right. So we're adding more protons in the nucleuses of these atoms as we go across, and the bonding electrons are not getting any further away from the nucleus, and so therefore, just like we learned in the periodicity chapter, the nuclear charge increases as we go across the periodic table. Therefore, it results in an increased attraction between the nucleus and the bonding electrons. All right, so that's very important to understand. All right, so if we go back to this, we can simply state this, that as we move across the periodic table, the electronegativity is going to increase, all right, get larger. As we go up a group in the periodic table, electronegativity increases. So electronegativity gets greater as we go up and gets greater as we go from left to right. Overall, fluorine is going to be the element that has the highest electronegativity. Make sure you write that down in your notes. And francium is going to be the element with the lowest or the least electronegative element. Okay? And so that's important to make note of in your notes. All right? All right, so we're essentially pretty much done with electronegativity for this lecture. Just make sure, honestly, that you really understand not only the periodic trend of electronegativity, but why that trend exists. And you're going to need to know that for the quiz because I'll ask you about it. All right, so one last concept we need to understand, and that is our last essential question, is how do we predict whether a compound between two elements will form a covalent or an ionic bond? And this is pretty simple. You just have to remember one number, and that's 1.8. All right, 1.8. Okay, now, if the electronegativity, let me reset, that's the wrong thing, highlight this. If the electronegativity between two atoms differs, so we have to subtract the electronegative values between two atoms that are being bonded. If they differ by up to 1.8, then it will at least be a covalent bond. All right? So there are two types of covalent bonds that we're going to look at in future lectures here. And those are nonpolar covalent and polar covalent. So it doesn't matter as long as the electronegativity values are 1.8 or less, the bond is going to be covalent. All right? Now, if the electronegativity values have no difference, then we're going to say, so no difference, then it's going to be a nonpolar covalent bond. But if there is a difference between electronegative values, then we will consider it a polar covalent. So just make note of that. Keep that in mind as we go into future lectures. But if the electronegative value is greater than 1.8, the difference is greater than 1.8, then it's going to definitely be ionic. Alright, so we can actually do a problem, an example problem real quick. If we go back to our periodic table and look at electronegative values, let's take and form a bond between, let's say, carbon and oxygen. So carbon has an electronegative value of 2.5 and oxygen of 3.5. So what's the difference between those two? So 3.5 minus 2.5 gives us a 1.0 difference. Well, that's less than 1.8, so therefore this has to be a covalent bond. So a bond between an oxygen and a carbon is covalent, right? Kind of see how that works? So let's erase this. Let's look at more like an ionic bond. Something like between lithium, it's not lithium, lithium, and let's say oxygen. Okay, the difference between those is 3.5 minus 1.0, and that difference is going to be 2.5. So it's much greater than 1.8, so therefore a bond between oxygen and lithium will be ionic. And so that's just kind of essentially how you treat using these electronegativity numbers to determine if a bond is going to be covalent or ionic. Okay? Now don't fret, you don't need to learn these values at all. You don't have to memorize them. You just need to know relatively the general trends, why those trends occur, and then if they give you the electronegative values, that you can take the difference between them and figure out if the bond will be ionic or covalent, just like we did here. Okay, and that's all there is to it. Alright, so we're pretty much done with this lecture. So what I would really strongly encourage you to do is to make sure that you've put down some great notes, study those notes, be ready for a quiz over this lecture in class. Again, I gotta stress the importance of two things: making sure that you understand electronegativity and making sure that you can calculate the delta H of a chemical reaction using bond enthalpies. Very important. Know those things when you come into class for the quiz. Other than that, we are done. So, adios until next time.